intelligent systems not only thinks for us, but also plans for us, optimizing every little step of the way, from streamlining business operations to solving complex logistical challenges. Artificial intelligence has been revolutionizing the art of planning. So, guys, today let's explore the intersection of planning and AI and how powerful is it in transforming industries and redefining possibilities. Hello, everyone. My name is Ms. Anushka Harshavardhan Nevgi from TYCAC Division A, and my roll number is 31. And this presentation has been prepared under the guidance of Professor Mrs. Ambika Gadkari ma'am. So, guys, this is what we are going to explore. In this session, we'll be seeing the foundations of simple planning agent, situation calculus, and what basic representation of planning consists of. Now, firstly, to know about planning, we need to explore what are the components of planning. So, planning, it's nothing but devising sequence of actions. To plan out something means to devise a sequence of actions. Like if we have an exam tomorrow, we'll first prepare a plan. Like how am I going to study? How am I going to cover my syllabus? This is nothing but planning. Now, why is planning important? It is important because the agent must operate autonomously in a complex environment. Agent is not being guided by anyone. It has to perform autonomously. And that is why we need planning. An example of planning would be solving an 8 puzzle game by generating a sequence of tile moves. Now, what are the different components of planning? The planning consists of states. States is like various different states. Like agent can go from one state to another, from another state to next state. That is nothing but states. Goal is nothing but your final state. What the agent wants to achieve is included in the goal state. The actions are the actions which are taken by the agent to traverse from one state to another in order to reach the goal state. Preconditions are the conditions which are given already, and the agent has to satisfy all of those conditions. And effects are various chain. Like if I do this, this will happen. It is nothing but the inference rules. Now, there are two types of planning environment. One is classical planning environment and the another is non-classical planning environment. The classical environment is deterministic. It is fully observable and finite and static. Finite and static means it is not dynamic. It's not going to change. It's fixed. It's going to stay as it is. It is fully observable. Fully observable means we have access to all the components of the environment. Nothing is hidden. Nothing is partial. Then comes the non-classical planning environment. They are partially observable or stochastic. That is, they're not deterministic. It's not a fixed outcome. There are no fixed inference rules. It requires advanced algorithm and agent designs. Now, a simple planning agent. Simple planning agent, it uses sensors to perceive and actuators to act. It is nothing but same to our expert system. It receives percepts from the environment. It processes those percepts to take an act, to plan the actions, like what it is going to do. If something happens, what action will it take? It executes action to change the environment, forms a perception action loop. Planning enables goal-directed behavior beyond simple reactions, and it determines future actions rather than merely reacting to the current stimuli. So a planning agent will plan for the future. It won't just take actions in the current state or like, reacting, reflexes. It's not made for reflexes. It is made for future actions, for planning. Then comes a stimulus calculus. Stimulus calculus, it sounds like a complicated concept, but it's really easy. It is a logic-based formalism used to represent dynamic words. Now we say move here, from here to there. Representing it in the form of logic is nothing but situation calculus. It models how action change situation state over time, a situation in history of actions rather than a static snapshot. It shows how it has gone from one state to another, how an action has taken place. Let's see the core elements. Core elements consist of actions, move, a table. Then there are situations. Situations is nothing but it is representing a particular sequence, a particular chain of something happening. And then lastly, the fluents. These are the conditions that can change. These are not constant. They keep on changing. As you can see here, the S1, S2, these are the situations. A is nothing but your action and the fluents are represented. One second. The fluents are represented over here. When we have an example of situation calculus. Let's study this example. Now, as we can see, the initial situation is this is the initial situation S0. On A, there's B, and on B, there's C. Now, the action is we move A comma table. What we are doing here is we are moving this A away from the B, and that is why it's over here. Now, the new situation is move A comma table S0. So this is another and this is another. Okay. And lastly, we are fluent update. We are applying the condition on A table and B table. That is why we are representing both, as there's this condition given is and. So we have this over here and this over here. Then what is the importance of situation planning? It's basically allowing us to represent what we say logic, right? So that logic is being represented in the form of actual preposition. That is why situation calculus is important. Then it helps us to give automated agents in the dynamic environment. It reduces the trial and error by stimulating actions outcomes before execution, and it provides a framework for handling uncertainty. Obviously, the agent is going to work in an uncertain environment, and that is why it will require a framework for handling that uncertainty. The last topic which we're going to cover in this presentation is the basic representation of planning. Like, how is planning represented? One way was the situation calculus. Now let's see how it can be represented in a more simpler way. Now we know planning is a process of choosing a sequence of actions to achieve a particular goal. As we have already heard or learned, to pass the exam, we have to have a plan. To do anything possible, like if you want to achieve anything, we should have a plan. A planning problem is typically represented as initial state, goal state, and actions. Obviously, there's some starting point, there is some ending point, and there are going to be actions, sequence of actions that is going to help us to achieve the goal state. Then the representations used, we have state space representation where the nodes are the states and edges are the actions. It is nothing but a graph representation. And then we have plan space representation. It focuses on partially ordered plans. Lastly, operators or actions, these are defined by preconditions. Like I've told you, preconditions are nothing but the conditions which are needed to be satisfied by the agent. And the effects are nothing but the inference. Like if I do this, this will be its effect. That is the effect. Plan, we've already known. Then comes planning domain. Planning domain is just for describing all the possible actions in the state. It's basically going to consist of all the states and actions. There is the planning problem. It consists of the initial state, goal state, and the available actions. Let's see an example. Action move A, B. It's telling to move A, B. So now what's happening over here is we're going to give some preconditions and we're going to give some effects. This is just an example. It can be anything of what we like. Your preconditions given are A should be clear as well as B should be clear. That is why we have the and sign. And lastly, the effects are on A, B, not clear B. B is not clear, A is clear. That's the effect when we shift A from B. Thank you.